All right, so this is part B of 1.3. We're taking a look at factor label. This is going to be a really, really important set of skills you develop. I know some of the problems we're going to do as examples here, and some of the problems you might see in homework won't be that particularly difficult. You can probably do a lot of them without using factor label. I highly recommend you use factor label, though. It's a skill that we're going to build on. It's a skill we're going to continue to use for several weeks, even months in chemistry. It's a really important skill to have. So build it now while the material is relatively easy. And then as it gets more difficult, you kind of have that skill set and it will be a little bit easier to work with. All right, so factor label. Factor label method, that method there. And again, the idea is this is just a problem solving method and it really just has to do with canceling out units. So $1 is equal to 100 cents. I think everybody's okay with that, familiar with that. But what this allows us to do, anytime we have equivalent values, $1 equals 100 cents, 100 pennies, is it allows us to write them mathematically like this, or like this. And these two things say the same thing. They're ultimately both saying this. There's $1 and 100 cents, or the exact, well, not necessarily the opposite, but just the inverse of that. There are 100 cents in $1. So how do we use that? And what does the factor label method look like? So let's say you have 9.6328 times 10 to the 8th cents, and we want to know how many dollars that is. Well, every factor label problem, we're going to start with a question mark. And then what are we looking for? We're looking for dollars. Question mark dollars is equal to, what do we have? So we always start with this. Here's what we're looking for, equal to, what do we have? And we have 9.6328 times 10 to the 8th cents. I like what's called the picket fence. That's where I draw a line, and I've got like the fence posts holding it up. The trick with factor label then is I need to cancel this unit out. So looking at my two options up here, I need cents on the bottom because I need cents divided by cents, and it'll cancel out, as opposed to cents times cents. If it's on the top, it ends up being cents squared. We don't want that. So I want to make sure I use this value here. So I have $1 on top, 100 cents on bottom, and there we go. My cents cancels out. We're left with just dollars. That's good. That's what I'd like. So now it's just time to crunch those numbers. Hey, great chance for us to use the big E button since we've got that exponent there. So I'll show you again how I'd recommend using that. Here, so you guys can see the whole screen. So I'm going to enter in my 9.6328. And I'm going to hit the second button up here. And then this button right here above 7, it's like the inverse button, but because I've got the second function on, I get the big E. So you see my value now reads 9.6328, big E, and now I just hit 8. That big E represents the times 10 caret. All that's taken care of, there it is. That's that number. Now I'm going to divide by 100. Any number on top we multiply, any number on bottom we divide. Don't necessarily have to do ones. We all know the identity property. So divided by 100, I press the enter button, and there we go. Almost $10 million worth of pennies. Quite a bit of money. Put a box around it. There we go. We're not particularly concerned with significant digits. This is an exact value. It's a definition. So we're not particularly worried about it. All right, so let's see another example here. Here's one that people get backwards all the time. a decimal point there just to show my level of significance, my level of measurement there. So if you're traveling 30 miles per hour, you're driving, I'm going to put a decimal after this one as well. That gives two significant digits. So you're traveling 30 miles per hour. How long in minutes will it take for you to reach or to travel, 100 miles? Well, all factor label problems start off the same. We say, what are we looking for? Question mark, minutes. We're looking for in minutes, time in minutes is equal to, all right, what did they give us? Well, they gave us two different numbers here. They gave us 30 miles per hour, and they gave us 100 miles. Whenever possible, choose the unit that just has the single unit. Choose the number, the value that just has the single unit. So I'm going to start with 100 miles. All right, so this is where people oftentimes get this type of problem mixed up. 30 miles per hour, so 30 miles in 1 hour. This is the exact same thing. That per sign is like that line right there. Or, and again, I think this is where some people get backwards. 1 hour, you can travel 30 miles. Again, these are saying the same exact thing. It just matters where we need our unit. I can travel 30 miles in 1 hour, or if I travel for 1 hour, I will travel 30 miles. Either way, they're saying the same exact thing. We just need to make sure we get the correct unit on bottom. I want miles to cancel out. Here we have miles on bottom. Miles cancels out. I'm left with hours. Now be careful. We're not looking for miles. We're not looking for hours. We're looking for minutes. So we actually have one more to do. I think this is probably a conversion we all know pretty well. There are 60 minutes in 1 hour. Hey, there we go. Now hours is canceled out. We multiply across top, divide out the bottom. So 100, I'm going to put my decimal point there. Divided by 30, I'm going to put my decimal point there. Again, I don't have to say the time point. If you want to, you can, but I just know that it's identity property. It's not going to change anything. And then times 60. And I'm left with 200. Minutes. Now I can't put a square on it. It's not my final answer. Look at my significant digits. I've got 3 there because the decimal point, I've only got 2 here. So I need to write 200 minutes with just 2 significant digits. There's really only one way to do that, and that's to put it into scientific notation. So take 200 minutes, so 2.0, there's my 2 significant digits. It's still 200. Make sure I put my unit out there. And there we go. If you're traveling 30 miles an hour, it's going to take you 200 minutes to travel 100 miles. Okay, well, we're going to use factor label a lot. Is when we use our metric conversions, our SI conversions. So you will need to know, you should already know, millimeters and kilometers. Question mark, we're going to KM. We have 1001 millimeters. Now, I strongly suggest going back to the base. If you know exactly how many millimeters are in a kilometer, you can do it in one step. It is possible. I like to go back to the base because I've only memorized what milli is to the base. So I know that there are 1,000 millimeters in 1 meter. So now I've got my base, and now I need to go from my base 1,000 millimeters. So sorry, 1,000 meters in 1 kilometer, because K is a bigger number. So there my base gets canceled out. And now I divide 1001 by 1,000 and by 1,000 again. significant digits on this one. I have the exact number I started with. Remember, zeros on the left, the leading zeros never count. So I've got the 1, the 0, and the 1. Those are my 4 significant digits, which is exactly what I started with. These are exact values here, so they're not going to change my number of significant digits. One more type of example, we've actually kind of worked with these, and that's density. We can also use density, or we can also use factor label to solve our density problems. So if an object has a density of 2.38 milliliters, what volume in milliliters would 6 grams of my object occupy? All right, so again, factor label, we always start off with what we're looking for. In this case, it's milliliters. What do we have? Again, we've got 2 values this time. Choose the one that just has the single unit. So this has grams and milliliters. Let's start with the one that just has the single unit. That's 6.0 grams. Now we can take our density, and we have to make sure, again, we've really got 2 ways to write that. We can say there's 2.38 grams in 1 milliliter, or same exact thing to say 1 milliliter would weigh 2.38 grams. Either way, they work just fine. We need to choose the one that has grams on the bottom. So that's going to be 2.38 grams on the bottom, 1 milliliter on top. And look at that, voila. One step, we've canceled out grams, divided out. We're left with milliliters. That's exactly what we're looking for. So we just have a quick division problem. 6.0 divided by 2.38 equals 2 significant digits, 3 significant digits. I'm limited to just 2 significant digits. That's the 2.5. So we'd expect 6 grams to have a mass of 2.5 milliliters. There we go. Hey, if this were a test, yes, I do want to see this type of work going on. You usually get 0.5 points for starting a problem off right, 0.5 points for choosing the correct number, and another 0.5 for choosing the correct unit. So that's worth a point. Another 0.5 here and another 0.5 there. So 0.5 for the 1 in the right place, a 0.5 for the correct milliliters in the right place. Down here then, 0.5 for the 2.38 and 0.5 for the grams. So we add all this up. Before we even got to the answer, we've got 1, 2, 3.5 points. So your work is worth 3.5 points on a test. You don't show units and you're down 1.5 of those points. So watch out for that. Your final answer, you're gonna have 0.5 for the calculation. So did you do the math right? You're gonna have 0.5 for the units and 0.5 for the correct number of digits, for a total generally of about 1.5 points for the answer. Okay, that means this is a 5-point problem, and 3.5 of those points, that's 70% of the total points, are in the work. So make sure you guys are showing your work. It is something I expect to see when I grade your tests, when I grade your homeworks. I need to see units, need to see work. Set it up like this. Take your time now while it's easy. It'll pay off big when it gets more difficult. All right, well, thanks for tuning in, and good luck preparing for the tests.